Okay, this is lesson 10.9 on Lagrange errors. So our textbook doesn't really refer to this as Lagrange error. Textbook refers to this as error estimate, but the AP exam talks about this as Lagrange error. So you can probably guess it's somebody really smart named Lagrange that figured out, oh, there's an error. So in the previous lesson, we talked about using the Taylor and Maclaurin series to really give us an estimation of some functions that we don't have access to back in the early 8 days, right? Of course, again, we have the calculator, so we know that calculator can give us some accuracy. But the calculator also uses those polynomials to give you those numbers, those estimations. So what Lagrange figured out is that, hey, using your Maclaurin or your Taylor series, you can get an approximation of the value, but there's some error, right? When you're comparing that to the actual sum, which you really can't get to because it goes to infinity, he figured out that the worst case your error can be is within some sort of bound. So that's actually pretty cool. And you get to see how good is your estimation, right? Because we know we can all find an estimation of certain things, but if you don't know how good your estimation is, then there's really no point. You want to know how good it is compared to an actual idea or an actual sum. That way you know then, is this method good, right? So how good is a Taylor polynomial? So in the previous lesson, we dealt a lot with a Maclaurin. This one we're going to deal with more with a Taylor polynomial. So Lagrange figured out that, hey, if you write out your series here, your Taylor polynomial, and you end it at a certain point, because you have to end at a certain point to give a finite sum, so it's like a partial sum. So then what is your error? Well, the error is actually here, right here. This is your error. The error is actually the next term. It's bounded within the next term. It is the next derivative, right, at the next power over the next factorial, right? But the only thing is you put in a z here instead of a c, and that z value is going to be determined later. Z right here says is between c and x, and we'll talk more about what that means in terms of our problem, right? Lastly, the error doesn't matter for the sign. It doesn't matter if it's positive or negative. It is the absolute value of your term. So if you get a negative value, it doesn't matter. You can just change to positive, because the positive and negative just kind of means that you're to the left or right of the actual sum, but we really don't know what that sum is. So that's why it doesn't really matter if it's positive or negative. Okay, so we only have one problem here. We're going to work this out. Hopefully you'll see all the ins and outs of how to do this, right? So it says find the Taylor polynomial with the remainder for the function f of x equals root x with c equals 4. C equals 4 tells me this is a Taylor polynomial because it gives you a constant here. If it's Maclaurin, it'll just say Maclaurin and it won't give you a c because c is 0, okay? And it does say n equals 3. So n equals 3 means we need the third degree polynomial. But because we're looking for the error estimate, you want to get one more than that. So when you set up your table, you want to set it up to n equals 4, because the fourth one is where the error or the remainder is going to be. Okay, so we'll set up a very similar table to Maclaurin like we did last time. So we have our function f of x equals root x. So we have n 0, 1, 2, 3, and I'm going to put a little squiggly for 4 because up to 3 is really what I want for my Taylor polynomial. That 4 is for my remainder. Okay, all right, and then your function is going to be f to the nth power of, or nth degree, nth derivative of your function, right? So because this is square root of x, it's a lot easier to write as a power. So x to 1/2 power, 1/2 x to negative 1/2, negative 1/4 x to negative 3/2, 3 over 8 x to negative 5 over 2, negative 15 over 16 x to negative 7 over 2. Okay, now nth derivative of 4, right? And now you can see it was Taylor, not a Maclaurin. If it's Maclaurin, you're going to plug in 0, then you don't have anything in this power series. Okay, so we're going to plug in our 4. We're going to get square root of 4 is 4. Sorry, square root of 4 is 2. And then you have 1/2 times 4 to negative 1/2. It gives you 1/4. You get negative 1/4. 2 to the negative 3, so that's 1/8. So negative 1 over 32. Here you have 3 over 2 to the 5, so that's 32 times 8. So you get 256 here. And then the next one, this one you do not figure out, because remember this is the z term here. So you have negative 15 over 16, z to the negative 7 over 2. Okay, now Taylor says multiply this by x minus 4, because that's what my c is, to the n power over n factorial. Okay, all right, First term will give you 2 times x minus 4 to 0 power over 0 factorial, which is just 1, so that's 2. 1/4 times x minus 4 to the 1 over 1 factorial, so x minus 4 over 4, okay? Negative 1 over 32, x minus 4 squared over 2 factorial. That gives me negative x minus 4 squared over 64. And then last but not least, 3 over 256 times x minus 4 squared over 3 factorial. Clean this up. You get x minus 4 squared over 512. Okay. You do need to do the last one. So you get negative 15 over 16, z to negative 7 over 2. Multiply this by x minus 4. Sorry, too big of a parentheses. So we have x minus 4 cubed over 3 factorial. Oh, sorry. We got 4. The previous one was wrong. That's right. 4 over 4 factorial. Make sure this is a 3. Okay, I caught my own mistake. All right. So clean this up. You will reduce out one of the 3's in here, right? So 3's in here, leaving you with a 5 here. So you have 5 x minus 4 to the 4th. And now you have 4. So you have 4 times 3 times 2. So 3 is gone. So 8 times 16. So 8 times 16, 128, z to the 7 over 2. Okay. So in terms of writing your Taylor polynomial, your function of root x is equal to 2 plus x minus 4 over 4 minus x minus 4 squared over 64 plus x minus 4 cubed over 512, and then your remainder of minus 5x minus 4 to the 4th over 128z to the 7 over 2. Okay, so in terms of your third degree Taylor polynomial, that's your answer. With the remainder, that's your remainder down here. So that usually you're not tasked to find that remainder on its own or attach it to your Taylor polynomial. Usually you're being tasked to find the third Taylor polynomial to the whatever degree or how many terms of the Taylor polynomial. So one thing I do want to caution you is if your n let's say your n equals 4. If there are zeros in your term, you don't include those, but then you may have less terms than the number of n. The most important thing is your power up here has to match the n that you're being tasked to deal with, right? If I say though, I want 4th term, the first four terms of your Taylor polynomial. If you have zeros within those first 4 terms, you cannot include those. So you got to keep going until you actually get 4 terms. So n equals 4 versus 4 terms, those are two very different ideas. All right. So again, n equals 4, you make your chart up to 4. If you have zeros in there, it's okay. You take what you have in your chart. If it wants the first 4 terms, then you gotta not include those zeros and keep going until you actually get 4 terms. Okay. Now, this next part is given to you. This is not what you make up. We actually provide you with this. So you are being asked in a question. So there's like a part 2 to the question, right? So part 2 question says, approximate square root of 4.03 and find the error estimate. Okay, so remember my c equals 4. I'm using that to approximate 4.03. That makes a lot of sense. It's very similar to when we did linearization. Linearization, we can't linearize, we can't approximate something super far away. Given that c equals 4, I'm not going to use that to approximate something that's like 16, right? So if I want to approximate, let's say 9.01, I would make sure that my c is 9 because I need to be close enough to it so I can approximate that number. Okay, so I'm asking approximate 4.03. So the idea is then you take your Taylor polynomial from before and you go ahead and plug it in. So root 4.03 is equal to 2 plus, all right, up here, I'm looking at my polynomial up here, right? So here at x minus 4, I am going to go ahead and plug that in. So 4.03 minus 4 is 0.03 over 4 minus 0.03 squared over 64 plus 0.03 cubed over 512, right? And you plug it into your calculator. Now, of course, keeping in mind the whole idea behind this is that back in the days, there is no calculator to use. You have a calculator, so yes, you can use it, but this is why this was powerful and useful back in the days, because this is able to give us some really, really nice accuracy, okay? So if you were to use your calculator, you should get a very, very cool answer of 2.07486. Now, you have a calculator right now, plug that into a calculator, you should be seeing that wow, when I plug this into a calculator, you get the exact same answer as this. So what does that tell you? It tells you that your number has very good accuracy, at least up to 8 digits of accuracy here. 1, 2, 3, or 6 digits of accuracy here, right? Maybe more. So how much more? How do we know? Well, we're going to look at our error. This is our error analysis. So what you want to do is now look at your remainder here and say, all right, -5, x is 4.03, so 4.03 minus 4 is 0.03 to the 4th power, all over 128, something to the 7 over 2. So remember, we said z is between c and x. Well, c is 4 in the problem, and x is what you're being tasked to approximate. So it's 4.03. What you want to do is you want to choose one of these endpoints, right? One of these, either the 4 or the 4.03, because those are my endpoints, and I know it's not equal to, but they kind of mark where your bound can be. Just like you know your asymptotes at pi over 2, but you can't draw your line. You will never reach pi over 2, but you draw a line at pi over 2 and say this is where it kind of meets its edge, right? So we're going to look at these two numbers, and looking at my fraction here, which one of these numbers will give me the biggest error, right? So because my z value is in the denominator, you want to choose a smaller denominator to get you the biggest value. So you put the 4 here, right? If your z value is up top, then you pick the bigger number, of course. So when you push this in the calculator, you will see your error is actually really nice. It's 2.472 times 10 to negative 10. So your error is very, very, very tiny. This is a very good approximation. When we did linearization, I believe our accuracy was only up to about 3 decimal places. This is a couple more than that, okay? All right. Last but not least is just an idea to remind you, all right? So just write this down. If a series is alternating, but truly alternating, not like the one we have up here. This one's not true alternating because you have positive, positive, negative, positive. So, you know, you need it to be positive, negative, truly alternating, okay? Then the largest error is the next term, regardless of the values of z and x. All right. So for example, my series is 2 minus 1 plus 1/2 minus 1/4 plus 1/8 minus 1/16 plus da 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 da. All right. And let's say I asked you to find me the sum, the approximation of this, right? So I'm asking you to use maybe the first 5 terms to find the approximation of whatever value I'm looking for. So if you're doing that, you use the first 5 terms, your error is the next one. This is your error. Your error is actually -1 over 16. You don't need to worry about plugging in the z or an x. So if you get your, actually, whatever the c value is, you plug it in already, right? So whatever the c value is, you plug in already, and you recognize that, oh, this is truly an alternating series. Then you stop at whatever end term they want you to stop at. Your error is going to be the next one. So you don't have to figure out the z value like we did up here, where you have to figure out the biggest bound, okay? If you're curious about why this is true, look at the notes for 10.5. At the very end, we talked about like the error analysis and like how good of an approximation we have when we have alternating series. Okay, all right, that's it, guys.